The next topic is about cell. So cell is a device that converts the chemical energy into electrical energy. So this is a simple sample of a cell here. This cell consists of one electrolytic solution, generally it is S2SO4, one of the example. Now it consists of two plates or two electrodes, we call it as. The first one is called anode, the second one is called cathode, and these are connected to external resistance or external body. Here I am taking a bulb as the external resistor, and this is connected to this one. Now, due to the reaction that are taking place between this, generally this is zinc, this is copper, so this is zinc and copper. So, due to the reaction here, electrolytic solution will give the energy for the charges to separate here. So the positive charge will reach here and the negative charges will be reached here. Generally what happens, the negative charges will flow through this one, that is electrons will flow through this wire, and they passes through the bulb and comes to this one when the key is closed and reaches this one. Once again, due to the chemical reaction, these electrons will travel here. So this is the direction of flow of electrons here, that is from anode to cathode. But in general what happens, we will think that the positive charge is passing because the direction of current is given by the direction of positive charge. The conventional direction of current is direction of positive charges. So this is the direction of current. So here the positive charge is moving along this wire and passes through this bulb. It will give the energy to this bulb to glow, and then it comes back, and here it will come here. Whenever this positive charge comes here, it will be attracted by this plate, and this will continue. This is a closed path. Now here, if we observe this one, we have different terms that we should remember. One is EMF, one is terminal voltage, the other one is internal resistance. So here I am going to take this as capital E, this is V, this is small r. So what is this EMF? Cell is a source of constant EMF but not the constant current. Why? Because by using this cell, always we will get a constant EMF, but the amount of current depends upon the external resistance also. So that's why we need to write here, cell is a source of constant EMF but not a source of constant current. The current coming from a cell does not depend upon its structure, it also depends upon the external resistance. That's why EMF is related to the cell. Now what is this electromotive force? So scientists they thought that this is a force required to move the electrons through the circuit, but afterwards they used this term without changing this one, electromotive force. This is not the force, remember this one, EMF is not a force, EMF is the work done to move the charges through the circuit. Here the electromotive force is the potential difference between the two terminals of a cell, between the two terminals of a cell when it is not sending any current through the circuit, any current through the circuit. So it is possible, let us say if you remove these wires, then they maintain a potential difference between these two. Without this external circuit, the potential difference between these two is called EMF, electromotive force. As it is a potential difference only, so this is measured in volts only. The SI unit of EMF is volts. Now, what is this terminal voltage? So we call it as this terminal voltage. Now what is this terminal voltage? This is also the PD, potential difference between the two terminals of a cell when it is sending a current through the external circuit or through the external resistor. Through the external circuit. So as it is also potential difference, this is also measured in volts only. Now the third one, the internal resistance of a cell. This is internal resistance. So what is this internal resistance? The opposition offered by the electrodes of a cell or the electrolyte of a cell to the flow of current to the external circuit. So there will be some opposition offered to this electric current to go out, and it will be opposed by whom? It will be opposed by electrolyte and electrodes. So the opposition offered by electrolyte as well as electrodes of a cell to the flow of current is known as internal resistance of the cell. The electromotive force of a cell only depends upon the nature of the electrolyte that we are using, whether it is H2SO4 or CuSO4. It depends upon the nature of the electrolyte that we are using. So whenever that electrolyte changes, the electromotive force of a cell also changes. And the second factor that changes this electromotive force, the electromotive force is metal that we are using for the electrolyte. We can use copper, zinc, aluminum. So we have different metals, but generally we use copper and zinc. Why? Because copper and zinc may produce the maximum electromotive force for a cell. But the electromotive force never depends upon these four factors. That is area of these two plates or area of these two electrodes. So area is not a factor here. The distance between two plates will not alter the EMF of a cell. So this is also not required. The quantity of the electrolyte that we are using here, whether you are using 1 liter, 2 liter, that is not a factor, and the size of the cell is also not a factor. So EMF only depends upon the nature and the metal that we are using for the electrolyte. But what about this internal resistance? What are the factors that can change the resistance or internal resistance of a cell? So here it depends on distance between two plates or electrolytes. Second one, area dipped in electrolyte. Third one, concentration of electrolyte. Fourth one, the temperature of that electrolyte. So internal resistance, which is measured in ohms, because as it is resistance, it depends on four factors. So now what happens to this internal resistance if the distance increases, area dipped in the electrode increases, concentration increases, and temperature increases. Here what we can write, the distance between two plates, if the increases, this is the distance between the two plates here. So if you increase the distance, then the length traveled, the distance to be traveled by the charges from one plate to another plate, it will be more. We know this formula R is equal to rho L by A. Whenever the length to be travelled is more, resistance is always more. So here, if you increase the distance between the two plates, then the distance to be travelled by the charges from one plate to another plate will increases. As the length increases, resistance also increases. So whenever the distance between two plates of a cell increases, internal resistance also increases. Second one, area dipped in the electrolyte. In this diagram you can see this is the portion which is dipped inside the electrolyte. If you dip more, then whenever area increases, the resistance will decrease. So we can write it is better to dip more area into the electrolyte. If the area is more, area dipped inside the electrolyte is more, then internal resistance will be less. Whenever area increases, internal resistance will decrease. Whenever the distance between two plates increases, resistance, internal resistance also increases. And the third one, concentration of the electrolyte. Whenever the concentration of this electrolyte is more, then more ions will be formed here. More ions are available when the concentration increases. More ions means more opposition will take place. That's why the internal resistance also increases. So whenever concentration increases, more ions will be formed or more ions are available now. For more ions, the opposition will be more. So opposition is called internal resistance. This also increases. And the fourth one, temperature. If you increase the temperature of this electrolyte by heating or by doing something, what happens? Whenever temperature increases, first the electrolyte will become thin. When the electrolyte becomes thin, due to this, the resistance will decrease. Now the internal resistance will decrease. So this is the case. Whenever temperature increases, the electrolyte will become thin and the ions can move freely, so that this internal resistance will decrease. So whenever this resistance decreases, more current will flow through the cell. So if you increase the temperature, the amount of current through a circuit will increase. Whenever current increases, the heat produced inside a circuit is given by H is equal to I square RT. So within the cell, as the current increases, the heat produced also increases. As heat increases, temperature increases further. So as a result, once again, the internal resistance will decrease and the amount of current will increase. When I increases, heat energy also increases as I square, H delta I square. So if you increase the temperature slightly, so this is just like a cycle. If temperature increases, due to this, the electrolyte will become thin electrolyte. Due to this, the internal resistance will decrease. Due to this, the current will increase. Due to this, heat energy increases. Due to this, temperature increases. Once again, if the temperature increases, electrolyte will become further thin and resistance will decrease and more current will flow through the circuit, and due to this, once again heat energy increases and temperature increases, and once again this will become thin. So this is just like a circuit. And here, so due to this, what happens? In most of the cases, these cells are kept in a place where there is a lot of ventilation. When it is exposed to the atmosphere or ventilation, then we can maintain the required temperature. When the ventilation is provided to this cell, it will lose the heat energy to the surrounding, so that we can maintain a constant temperature. If you fail to maintain this temperature constant for a cell, what happens? As the heat energy increases, the cell may burst. So this you can see in case of Samsung Galaxy 7, and even now so many airports or aeroplanes, they are not allowing this Samsung Galaxy 7. Why? Because it happens so many times to this Samsung Galaxy 7. As we are charging this Samsung Galaxy 7 cells, generally the same cycle takes place. Whenever we are charging this one, temperature is increasing within this cell and the electrolyte is becoming thin and resistance will decrease, current increases, heat increases, it will repeat, and due to the loss of this lot of heat produced in these cell phones, and they are bursting. That's why most of these airports, they are not allowing these cell phones, and it happened to Nokia also previously around 10 years back. So that's why it is better to maintain a constant required critical temperature for the cell to operate at its best efficiency. Discharging of a cell, here the cell of EMF E and the internal resistance R. This is a cell here. It is connected to a external resistance of resistance R, and it is connected via key. So when the key is closed here, the current flows from the cell through the external circuit and once again enters into this cell. So let me take the current flowing through this circuit as I. So how to find out I value here? The current is given by, actually current, it flows from the circuit. Let us say this is A, it moves along this path, it comes to this point B. Let us say that somewhere here this point is C here. So externally the current is flowing from A or B, and internally current is flowing from B to C via B to A via C. So this is cathode, this is anode. So current flows from cathode to anode when the cell is discharging. That means cell is giving the charge to the external circuits. So while discharging, current flows from cathode to anode within the cell, but the current flows from anode to cathode outside the cell. So this is within the cell, direction of current is from cathode to anode. External to this one, current is flowing from anode to cathode. So this is the first point. Now how to find out the current through this circuit here? I is given by total EMF by total resistance of this circuit. This is capital R plus small r. So this is capital R plus small r. By cross multiplication we will get E is equal to I capital R plus I small r. This IR is the potential drop between these 2 points or across the resistor. So we can write E is equal to V plus IR. This is the expression to find out the EMF of a cell when it is discharging. Suppose if you take the charging of a cell, we do this daily to charge our mobile phone, to charge our laptop. We will use a source. If the potential of this source is greater than this EMF, let us say this is a 10 volts battery and I need to connect a 230 volts battery here, 230 volts source here, then only current flows from high potential to low potential. Let us say this is 10 volts cell inside our phone, but if it is only 8 volts, if you want to charge this one, current never flows from low potential to high potential, current flows from high to low. So condition is, to charge any cell, the external source should have more potential than the cell. So that is the condition here. To charge any cell, the external source should have a PD or potential more than EMF of the cell that we are going to charge. Now in this case, here also we have a key here. If you close the key, now this battery or the cell will be charged by the current given by this external resource or source. So now the current will flow like this, current will go like this, here it enters, it leaves in this circuit, and it will continue in this one. During discharging, current is flowing from cathode to anode within the cell. But when we are charging the same set of the same cell here, current is entering from anode to cathode. So direction of current here is current flows from anode to cathode within the cell. This is within the cell, but outside the cell it is from cathode to anode, exactly opposite to the circuit. So this is within the cell. Now here, how to find this current? To find out this current, the current is given by, according to Ohm's law, potential difference by resistance. So this is at high potential, this is at low potential. So the potential difference between these two is V minus I. By the only resistance in this one is the resistance of the cell that we are charging. So by cross multiplication we will get V minus E is equal to IR, V is equal to E plus IR. So from this formula we can say V greater than E. So the potential of the battery should be greater than the EMF of the cell to be charged. But during discharging, EMF is greater than potential difference, while charging, potential is greater than EMF of the cell. When the cell is delivering the current, when cell delivers this current or discharging, when cell is delivering the current, we can write PD less than EMF, whereas when we are charging this one, PD greater than EMF. You can see this one here, the cell is doing some work. Cell is doing some work, that means it is sending the charge or current to the external circuit. So discharging means work will be done by the battery, work done by the cell. Whereas charging of a cell means some external source is doing some work on the cell. This is work done on the cell. Work done on the cell. So how to find out this work done by the cell? Work done is given by potential difference into charge. So if you know the amount of charge flowing through this one, this work done by the cell, work done by the cell is given by the charge that is flowing into the EMF of the cell. This formula already we used while calculating the work done by the battery in capacitors. So if you know the amount of charge flowing through the circuit, and if you know the potential or the EMF of this one, we can find the work done by the cell. If you consider any cell here, so let me take a cell here. This is a cell of EMF E and the internal resistance is R. So this is a cell. As a whole, we will denote this as the cell here. In some problems, sometimes the cell may be given like this only. That means it has no this is internal resistance R. If internal resistance of a cell is 0, then the cell is called a ideal cell. Please write down this point. For an ideal cell, the internal resistance will be taken as 0. Now, suppose if you take a cell here, internal resistance R, EMF E, and if you join this and this here, these are the two ends of the cell. If you join this with a thick conducting wire, this is a thick conducting wire. Why I am telling thick conducting wire? When the thickness of the wire is more, cross-sectional area will be more. So here this cross-sectional area, this is a thick conducting wire. When the thickness is more, we know that R is equal to rho L by A. When area is more, resistance will be less. For a thick wire, resistance, as area is too high, resistance will be too small. So we can write, for a thick conducting wire, the resistance is taken as nearly 0. Now, what is the amount of current flowing through this circuit when it is connected, when the two ends of the cell are connected with the thick conducting wire? We can write current I is equal to total EMF by the total resistance in this circuit. We are using the same one as it is a discharging current. Now, in this, what we have to substitute, EMF is E, internal resistance is R, and the external resistance is 0. So, the current will become E by R. You can see this formula, current when it is discharging is given by total EMF by internal resistance plus external resistance. Whenever the external resistance decreases, the denominator will decrease, current increases. So what is the maximum current that is passing through a cell or given by a cell means whenever this becomes 0, because internal resistance may be 0 for an ideal cell. But here, let us say for a given cell, it is not an ideal cell, for a given cell, the external resistance is 0, then the current will become E by R, and when compared to this one, this is maximum current, so this is the maximum current. And this is called a short circuit. Why? Because the two terminals of a cell must be connected with the help of a resistor here. But here resistor is 0, that's why we can write this current is also called a short circuit current. And this is the maximum current that cell can give. Now, similarly, if the same circuit, same diagram here, I am going to draw here. This is E, internal resistance R, and the two ends are left like this. Now here, when a wire is connected, the internal resistance, the resistance of this wire, thick wire is 0. Here no wire is connected. So what is the resistance here? Here there is no wire means the area of cross section of that one is 0. That means here nothing was there. So the resistance can be taken as infinity. Here I am going to write the external resistance is infinite. Whatever the current that comes here cannot pass through this one. That's why here I can write the external resistance when it is left alone. When no wire is connected between these two, then resistance should be taken as infinite. So now the current is given by E by R plus capital R is infinite here. Why? Because it is left alone. Now this will become E by infinite, which is equal to 0. That means no current flows here, and this is called an open circuit. So current is 0 in an open circuit. Whenever a circuit is open, no current flows through the circuit. That means for the current to flow, the path should be a closed one only. As it is open, no current will flow. So current is 0 in a open circuit. When nothing is connected between the two terminals of a cell, we can write this formula E is equal to V plus IR. We know as there is no current, this I will become 0. So E is equal to V. That means this is the definition of the EMF of a cell also. The EMF of a cell is the potential difference between the two ends of the cell when no current is passing through this one. Why? Because here in open circuit current is 0. So the potential difference between the two ends of the cell in open circuit is called EMF. So we can write EMF as EMF is the potential difference between two terminals of a cell in open circuit. So we can write this as when it is not sending any current through the circuit. Similarly, if you take this one, the potential difference here, V is equal to IR, as the external resistance is 0, the PD will be 0 if the two ends are connected with the help of a thick conducting cell. So here potential difference or terminal potential difference between the two terminals will be 0. The next topic is grouping of cells. Suppose if you want to need some EMF which is greater than the EMF of a single cell, then we can connect these cells in series combination. Please remember this point. In series combination, of cells, when we are connecting 2 or 3 cells, let us say this is first cell, this is a second cell, this is E1 R1, this is E2, this is internal resistance R2. So this is called a series combination of cells. EMFs are additive or subtractive, but internal resistances are always additive. So in this case, if you see these two cells, negative terminal of the first cell connected to the positive terminal of the second cell here. So when these two are connected like this, these are said to be connected in series. The net EMF in this case is given by E1 plus E2. So this is equal to E1 plus E2. So these two are additive here. By adding the EMF of two individual cells, we will get the net EMF of this combination. What about the R net here? As these two resistors are in series, we can write R net is equal to R1 plus R2. But if these two cells are connected such that this is the first cell of EMF E1 and internal resistance R1, and this is the second cell of EMF E2 and internal resistance R2. Now it is different from the previous one. This is also series combination. Negative terminal of the first cell is connected to negative terminal of the second cell, whereas here the negative terminal connected to positive terminal of the second cell. So now these are also said to be connected in series only. The condition is, what is E net now? E net is given by E1 minus E2 or E2 minus E1. It is E1 minus E2 if E1 greater than E2. Suppose if E2 is greater than E1, this equation can be written as E2 minus E1. Whereas R net, the resistance in this combination is always additive. So here it may be additive or subtractive, but internal resistance or net resistance is always additive. So in both cases, R net is equal to R1 plus R2 plus R1 plus R2. Even though the positive terminal of the second cell is connected to negative terminal of first cell, or negative terminal of this one is connected to negative terminal of second cell, R net remains as R1 plus R2 only. But this formula, the net EMF will change. About the series grouping of cells and parallel grouping of cells. Here in series grouping of cells, first we are going to connect n identical cells in series to an external resistance capital R. So this is capital R, this EMF is E, this is also E, this is also E, and this is also E. And resistance of internal resistance of this one is R and R respectively. Here n similar cells of EMF each and internal resistance small r each connected in series. So what is the equivalent EMF of the series combination or series grouping? Equivalent EMF of the combination is given by This is E. As we said earlier, we can add this. It may be additive or subtractive, but here negative connected to positive, negative connected to positive, negative connected to positive, and so on. So the equivalent EMF of this series combination is given by E plus E plus E and so on E. As there are n similar cells, the total net equivalent EMF is given by NE. Similarly, what is the equivalent resistance or internal resistance of the combination? So equivalent internal resistance of the combination, which is given by R equivalent is given by R plus R plus R and so on R, which is given by, as there are n similar cells, we can write this as NR. This is equivalent EMF, this is equivalent internal resistance. So what is the current that is coming from this one, from the series combination of cells? Let the current, we call this current as main current, that is current given by the series combination of cells. Remember students, the combination of two or more cells is called battery. So this we call it as a battery. Battery is a combination of two or more cells. So battery is the two or more cells connected in series or parallel is known as battery. Now from the battery, how much current is coming? I. This current we call it as main current. So the main current is given by I is equal to the net equivalent EMF, that is NE, by the net resistance of this circuit. The total resistance of this circuit, internal resistance, is given by here. This is NR plus R. So this is given by the total main current of this circuit, or the current given by the battery to the external resistance. If you know the equivalent EMF, equivalent internal resistance, this is the net resistance of the combination. You can find total EMF by total resistance will give the total current or main current. Now if you know this value, we can find power consumed by external resistance. Before that, let me find out the PD across, potential difference across external resistance. V is equal to I into R. What is this I value? NE by NR plus R. So this can be written as NE by R plus NR into R. This is the PD across the combination. So potential difference across this combination, that amount of current into this resistance will give PD across the external resistance. Now the power consumed by the external resistance. Power consumed by external resistance, by external resistance, that is capital R, is given by P is equal to, as these are connected in series, the same current passes through each cell. So current will be same. Power is given by power P is equal to V square by R, I square R. Here I am going to use power is equal to I square R. That is power, this current is NE by NR plus R. So I am going to write NE by R plus NR whole square into R. So this is the power consumed here. But what is the maximum power that can be consumed? When does this circuit will consume maximum power? For the power to be maximum, this denominator should be minimum. So from this we can write the circuit or this external resistance will consume maximum power when the denominator is less, or this value should be, if capital R is equal to NR, then power consumed will be maximum. So this we will discuss in the next topic in maximum power consumption theory. So there we will discuss about this power as well as the maximum power consumed. Now we come to this parallel combination of cells. In parallel combination of cells, once again here I took n similar cells, and here also I am going to take n similar cells which are connected like this. And this is connected to one external resistance capital R. So these are the internal resistances which are given by small r, small r, small r, small r each, and the EMF of each cell, because I am connecting n similar cells in here also. For n similar cells of EMF capital E and internal resistance small r each, connected in series, connected in parallel now, connected in parallel. So how to find the equivalent EMF of the combination? The equivalent EMF of the combination is given by equivalent EMF of the combination is given by, as we know that in parallel combination potential difference remains same across each branch, so the EMF is also remains same. So E equivalent is given by just E only. This is the equivalent EMF. Now what is the equivalent internal resistance? The equivalent internal resistance of this combination is given by, as these are connected in parallel, so this R equivalent is given by R by N. Whenever similar resistors are connected in parallel, total effective resistance will become a single resistance by number of branches in that parallel combination. Now what is the main current that is given by this one to the external resistance? So we will write this as main current is equal I is equal equivalent EMF by total net resistance of this combination, which is given by E by, this will become R by N is the total effective internal resistance plus the external resistance capital R. If you take LCM here, this will become NE by R plus NR. This is the main current that is passing or that is coming from this battery. Why? Because whether they are connected in series or parallel, a combination of cells is always called battery. So this is also a battery. Now after finding the main current, what is the PD across external resistance? PD across external resistance, which is given by V is equal to I into capital R. We know the main current that is coming from the cells. This is NE by R plus NR into capital R. Now, similarly, what is the power consumed by the external resistance in this point, in this grouping? Power consumed by external resistor is given by P is equal to, as it is a parallel combination, we should not use this formula. Power is equal to I square R for series combination, as I is constant. Here V is constant, you can write V square by R. We know the potential difference across the external resistance, which is equal to NE by R plus NR into R. This is potential, but squaring on this one and dividing this one, so you will get the power consumed by the external resistance as like this. Now here also the maximum power consumption theory I will explain later. Now when this series combination is helpful for us and when we will use this parallel combination, the series combination is helpful only if the external resistance capital R is much greater than the total effective or equivalent internal resistance. So series combination is useful if external resistance is greater than NR. But what about this one? Parallel combination is useful if NR is greater than capital R. Series grouping of cells, if the cells are different In the previous explanation, we took n cells of equal EMF and equal internal resistance. But now this will be E1, E2, E3, En. This is Rn, R1, R2, R3 and so on. And external resistance is capital R. Here, in this, how to find out the effective EMF or equivalent EMF? The equivalent EMF is given by the sum of the EMF. All cells are connected in the same sense. If the cells are different and connected in same sense. So what is this sense? Sense is negative terminal of the first cell is connected to positive terminal of the second cell. Negative terminal of the second cell connected to positive of the third cell and so on. Then it is called same sense. That means all the cells will produce current, all the cells positive terminals will produce current in the same direction. Same sense is nothing but current from each cell is flowing in same direction. Current from each cell flows in same direction, then they are called same sense. So here all the positive terminals are connected towards left, negative terminals are connected towards right side. So then E equivalent is given by, this will be equal to E1 plus E2 plus E3 and so on En. So this is the equivalent EMF of this combination. So what is the effective equivalent internal resistance or R equivalent internal resistance is given by R1 plus R2 plus R3 and so on Rn. So this is equivalent internal resistance. So what is the main current that is coming from this battery? So the main current in this case is given by I is equal to E equivalent by R equivalent plus external resistance. Why? Because we should not forget this external resistance whenever we are calculating the current through the circuit. So this I is given by E1 plus E2 plus E3 and so on En by, this will be R1 plus R2 plus R3 and so on Rn plus the external resistance that is connected in series with this combination. So this is the main current. Similarly, if you consider the parallel grouping of different cells, here the cells are different here, not identical. So now if you connect this one, this is E1 with internal resistance R1, this is E2 with internal resistance R2, this is E3 with internal resistance R3 and so on. And so many cells are connected like this. And the last cell in this combination, let us say this is En with the internal resistance Rn. So this is connected to an external resistance capital R like this. Now, as the cells are different here, but once again these are connected in the same sense. Why? Because all positive terminals are connected on left side here. All positive terminals are connected to one point, all negative terminals are connected to this point. Then they are said to be connected in same sense. So in this case what happens? The net EMF is given by, here let us say the current given by the first cell is I1, second cell is I2, third cell is I3 and the nth cell is In. This is the total current. So we know that the total current is the sum of the currents given by each and every cell in this combination. So I can write I as I1 plus I2 plus I3 and so on In. But how to find the net EMF, net current? Net current is given by E net by R net here. So this is the total current. This is given by E1 by R1 plus E2 by R2 plus E3 by R3 and so on, En by Rn. Now, E net is given by E1 R1 plus E2 R2 and so on, En Rn into, this will become R net. But what is this R net? Here all these cells are connected in parallel. 1 by R net is given by 1 by R1 plus 1 by R2 plus 1 by R3 and so on, 1 by Rn. This is R net. This can also be written as E net or E equivalent is equal to E1 by R1 plus E2 by R2 and so on, En by Rn by. This R net, when it comes this side, this will become 1 by R net. This 1 by R net value I can substitute here. Therefore, the total equivalent EMF of this parallel combination is given by, or net EMF is given by E1 by R1 plus E2 by R2 and so on, En by Rn by. This will become 1 by R1 plus 1 by R2 plus 1 by Rn. So this is the net effective EMF or equivalent EMF of the parallel combination. This is EMF, this is R net. So by using this you can find out the current flowing through this one, which is equal to the ratio between the E net by R net. You can observe one point here. While calculating the current through the series combination, I used this external resistance. But while calculating the current through the parallel combination, I am not considering this R. Why? Because the parallel combination is useful only if this total effective resistance, that is R net, is much larger than capital R. So this capital R can be neglected. That's why we will get this formula. Similarly, in some problems, especially in competitive exams, sometimes if you take n similar cells, if one of the cell is connected wrongly or two of the cells are connected wrongly, then the net EMF will change, but net resistance will not change. As a result, current will also change. Now, for that, what we are going to do, if the cells are not different, let us say these are identical. If cells are identical, and I am going to take n cells are identical and m cells in that combination is connected wrongly. M cells are connected wrongly. So then what happens to the EMF, what happens to the internal resistance, and what happens to the total current flowing through this circuit? Now I am going to take the same similar cells here which are having the same EMF and the same internal resistance. But here what happened, in this combination, some cells are connected wrongly. Wrongly means here negative terminal connected to positive, negative terminal of the second one connected to the positive of the third one, and so on. But some cells are connected in the combination like this. So negative connected to negative directly. Let us say out of n cells, m cells are connected in the opposite polarity or opposite sense. Now, what is the equivalent EMF of this combination? Total EMF of this combination when they are connected in the same sense is equal to Ne minus, if one of the cell is connected wrongly, the effect will be seen in case of two cells. For example, let me take two cells here. This is EMF E, this is EMF E. Now, negative connected to negative, the net EMF will be E minus E. Why? Because negative connected to negative, so net EMF will become 0. That means if one cell connected wrongly in a two cell combination, the net EMF of this one will become 0. It cannot give any current to the external circuit. Similarly, let me take 5 cells here. Out of 5 cells, 1, 2, 3, one is connected wrongly, only one is connected wrongly. So this is E, this is E, this is E, this is E, this is E. So what is the net or equivalent EMF in this combination? We can write this as E plus E plus E, as it is connected in the wrong polarity or reverse polarity or wrong sense or reverse sense, we can write minus E plus E. So whenever out of 5 cells, if one cell is connected wrongly, the effective EMF will not become 4E. Instead of that, this will become 3E only. That means one cell will spoil one more cell in the series combination. Here also, when m cells are connected wrongly, the effect will be 2m cells will be nullified. So total EMF will become total number of cells into EMF of each cell minus 2 times the wrongly connected cells. This is the number of the cells connected wrongly into EMF. So this can be written as the total EMF of each cell is into number of cells in this series combination minus 2 times of m, where m is the number of cells that are connected wrongly. So equivalent EMF will become n minus 2m into E. But what about the equivalent resistance here? Resistance cannot be negative at all. So that's why in case of EMF, I am writing n minus E. But in case of equivalent internal resistance, as there are n cells, each cell is having internal resistance R. So we have to add all these resistors, whether they are connected in the same polarity or reverse polarity. The total resistance will become NR only. So this is E equivalent, this is R equivalent. Then what about the current? The current is given by N minus 2M into E by NR. But whereas if all the cells are connected in the same sense, the current would have been, this will be NE by NR plus this capital R. Here also you can write NR plus capital R to find out the current if the cells, some of the cells are connected in the reverse polarity.